Imagine standing at the edge of everything you know. Not at the edge of a cliff, not at the shore of an ocean, not even at the boundary of a continent, but at the very threshold of human comprehension itself. Imagine looking up at the night sky and realizing, with a cold and beautiful terror, that every single star you can see, every pinprick of light that has ever inspired a poem or guided a sailor home, every constellation that has ever been traced by trembling human fingers across the dark, all of it, every single one of those stars, is almost incomprehensibly small compared to what else is out there. Compared to what the universe has been quietly, patiently, catastrophically building for the last 13.8 billion years. We are living inside the greatest construction project in the history of existence. And we haven't even begun to understand the blueprints. Tonight, we are going to talk about structures. But not the kind of structures you are used to thinking about. Not the Eiffel Tower, not the Great Wall of China, not even the International Space Station, which orbits our planet at 17,000 miles per hour and still seems impossibly grand when you see it cross the night sky. We're going to talk about structures so enormous, so breathtaking, so fundamentally reality warping in their scale, that the moment you truly grasp what they are, something changes in you. Something shifts. You will never look at the sky the same way again. You will never feel entirely safe in your assumptions about the size of things. And you will be left with one question burning at the back of your mind, a question that has haunted astronomers, physicists, philosophers, and dreamers for generations. If the universe can build things this big, this violent, this strange, what else is it hiding? Let us begin at the beginning. Or rather, let us begin where the beginning ended. About 13.8 billion years ago, in the first fraction of a second after the Big Bang, the universe was a place of unimaginable density and heat. Everything that exists today, every galaxy, every star, every planet, every atom in your body, every thought you have ever had, was compressed into a space smaller than a single proton. Then it expanded. Not exploded outward into empty space, the way a bomb explodes, but expanded, the very fabric of space itself stretching in every direction simultaneously. Within the first 3 minutes, the universe had cooled enough for protons and neutrons to form. Within 380,000 years, electrons joined those nuclei and the universe became transparent for the first time, releasing a glow of light that we can still detect today. The cosmic microwave background radiation, the oldest light in existence, a faint echo of the universe's infancy that fills every inch of space in every direction. And then, slowly, over hundreds of millions of years, gravity did something extraordinary. It pulled. It gathered. It clumped. In the vast, dark silence after the Big Bang's afterglow faded, tiny fluctuations in the density of matter began to grow. Slightly denser regions pulled in more material. More material meant more gravity. More gravity meant more material. It was a feedback loop stretching across cosmic time, and the structures it built, the structures we are about to explore together, are the universe's greatest masterpieces. And its greatest monsters. Ask yourself this, right now, wherever you are sitting or standing or lying as you listen to this. What is the biggest thing you can picture in your mind? A mountain? A planet? Our solar system, stretching from the sun to the distant, frozen shores of the Oort cloud, a bubble of icy debris that extends perhaps 1 to 2 light years from our star? Go further. Our galaxy, the Milky Way, a spiral of 300 billion stars, 100,000 light years across. So vast that light itself, traveling at 186,000 miles per second, would take 100,000 years to cross it from one end to the other. Now stop. Take that image in your mind, that swirling, beautiful, incomprehensibly vast galaxy, and understand that compared to what we are about to describe, the Milky Way is little more than a grain of sand. Less than a grain of sand. A speck. A whisper. This is not hyperbole. This is the universe. Let us start with something relatively close to home, cosmically speaking, because even the structures in our own cosmic neighborhood are enough to make the mind reel. And we will build from there, step by extraordinary step, until we reach the very largest structures ever discovered. Structures so vast they challenge our fundamental understanding of how the universe is allowed to work. The first megastructure we need to talk about is one that most people have heard of, but very few people truly appreciate in all its ferocious, magnificent, terrifying glory. We are talking about our sun. Not the sun as a warm, pleasant source of daylight and vitamin D, but the sun as the engine of devastation and creation that it truly is. The sun is a thermonuclear reactor roughly 1.4 million kilometers across. If you hollowed out the sun and filled it with Earths, you could fit approximately 1,300,000 of them inside. Every single second, the sun converts roughly 600 million tons of hydrogen into 596 million tons of helium. The remaining 4 million tons every second, are converted directly into energy according to Einstein's famous equation, E equals mc squared. That energy radiates outward in all directions, and a tiny, vanishingly small fraction of it falls on our planet and sustains all life on Earth. Now here is the thing that people rarely stop to appreciate. The sun is a remarkably average star. It is sitting somewhere in the middle of the stellar mass range. It is not particularly young, not particularly old. It is a yellow dwarf, a common type, unremarkable in the grand catalogue of stars. And yet we would have to travel 4.2 light-years to reach the nearest other star system, Alpha Centauri. A journey that with our current technology would take approximately 75,000 years. The emptiness between stars is so vast, so absolute, that the sun's immensity barely registers on the scale of the Milky Way. But even the sun is not what we came here to talk about. We came here to talk about things that make the sun look like a firefly. Things like VOID Canis Majoris. VOID Canis Majoris is a red hypergiant star located approximately 3,800 light-years from Earth in the constellation Canis Major. For many years, it was considered one of the largest stars ever discovered. And when you look at the numbers, it is immediately apparent why. VOID Canis Majoris has a radius of approximately 1,400 times the radius of our Sun. If you placed VOID Canis Majoris at the center of our solar system, where the Sun currently sits, its surface would extend beyond the orbit of Jupiter. Jupiter, the planet that is so large that all the other planets in our solar system could fit inside it with room to spare. Jupiter would be swallowed, buried deep within the body of this single star. Saturn would be engulfed. Mars would be gone. Earth would cease to exist as anything other than a memory. Imagine trying to wrap your mind around that. Imagine standing on an imaginary platform orbiting at Earth's current distance from the Sun, 93 million miles, and looking up, not at the small white disk of the Sun as we know it, but at the surface of VOID Canis Majoris surrounding you in every direction, a wall of churning, boiling plasma stretching from horizon to horizon and beyond, in every direction, in every dimension. You would not be orbiting a star. You would be inside one. And VOID Canis Majoris is not even the largest star we know of. That title, at the time of our best measurements, belongs to candidates like UY Scuti or Stephenson 218, stars with radii estimated at between 1,700 and 2,100 solar radii. Though these measurements are difficult to make with precision and are subject to revision as our instruments improve. The point stands. Stars can grow to sizes that are simply, fundamentally impossible to visualize on any human scale. But stars, even the most monstrous of them, are not the megastructures we are truly here to discuss. Stars are the bricks, the mortar, the individual components of something larger. We need to talk about what gravity builds when it has billions of years and billions of stars to work with. We need to talk about galaxies. The Milky Way, our home galaxy, is a barred spiral galaxy approximately 100,000 light-years in diameter, containing somewhere between 100 billion and 400 billion stars. Scientists have revised this number upward several times as our instruments have improved. 400 billion stars. If you tried to count them at 1 per second, without stopping, without sleeping, without taking a single breath, it would take you approximately 12,000 years to reach 1 billion. To count 400 billion would take you close to 12,000 years multiplied by 400. nearly 5 million years. Our species has only existed for roughly 300,000 years. The scale mismatch is almost comical in its extremity. But even the Milky Way is not alone. It is part of a group. Not a small, cozy group, though by cosmic standards it actually is relatively modest, called the local group. The local group contains more than 50 galaxies, including our own Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller satellite galaxies. The Andromeda Galaxy is our largest neighbor, a spiral galaxy containing approximately 1 trillion stars, located approximately 2.5 million light-years away. 2.5 million light-years. The light reaching your eyes from Andromeda right now, if you look at it tonight in a dark sky as a faint smudge barely visible to the naked eye, left that galaxy 2.5 million years ago. Before our species existed, before Homo sapiens had walked the Earth, before the last ice age, before much of what we would recognize as human history had even begun to unfold. That light has been traveling at the speed of light for 2.5 million years, and it just now arrived at your eye. Now, here is something that most people do not know about Andromeda, something that should make the hair on the back of your neck stand up. Andromeda is moving toward us. It is hurtling through space in our direction at approximately 110 kilometers per second. That is 68 miles per second, or about 250,000 miles per hour. In approximately 4.5 billion years, the Andromeda Galaxy and the Milky Way will collide. They will interpenetrate each other, their stars and gas clouds and dark matter halos mixing in a slow, catastrophic, beautiful cosmic dance that will take billions of years to resolve. The collision itself is unlikely to result in direct stellar collisions. Space between stars is simply too vast for that to happen frequently. But gravitational forces will fling stars into wildly different orbits, distort the shapes of both galaxies beyond recognition, and eventually produce a single, massive elliptical galaxy that astronomers have already given a name, Milkomeda. Think about that. The galaxy in which you live, the galaxy that contains every star you have ever seen with your naked eye, is on a collision course with the largest structure in our cosmic neighborhood. And the deadline for that collision is set. The clock is ticking. It has been ticking for billions of years. 4.5 billion more years from now, the night sky as seen from whatever world might exist at that time will be transformed into something our ancestors could not have imagined. A sky blazing with a combined light of two galaxies merging into one, new stars being born in enormous bursts as gas clouds collide and compress, the architecture of our cosmic home being completely, irreversibly rebuilt. But we are still only looking at our local neighborhood. The local group itself, those 50-plus galaxies, occupies a region of space roughly 10 million light-years across. A 10 million light-year bubble. And that bubble is a suburb, a quiet backwater, of something far, far grander. The local group is gravitationally bound to a structure called the Virgo supercluster, also known as the local supercluster. The Virgo supercluster contains more than 100 galaxy groups and clusters, all dominated by the Virgo cluster at its center. A vast collection of over 1,300 galaxies crammed into a region of space about 15 million light-years across. The Virgo supercluster as a whole stretches approximately 110 million light-years from one side to the other. 110 million light-years. If our fastest spacecraft, Voyager 1, which has been traveling through space since 1977 and is currently moving at roughly 38,000 miles per hour, were pointed at the far edge of the Virgo supercluster, it would take roughly 2 quadrillion years to get there. The universe itself is only 13.8 billion years old. We are talking about timescales that make the age of the universe look brief. But here is where things truly begin to spiral into the surreal. Because in 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii made a discovery that fundamentally reframed our understanding of cosmic geography. They published their work in the journal Nature, and it revealed something that had been hiding in plain sight, invisible not because it was far away, but because it was simply too large to see all at once. They discovered that the Virgo supercluster, that 110 million light-year behemoth we had already been impressed by, is itself just a small tendril, a single lobe, of a vastly larger structure they named Laniakea. a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters. It contains approximately 100,000 galaxies. Its total mass is estimated at approximately 10 to the power of 17 solar masses, 100 million billion times the mass of our Sun. It stretches approximately 520 million light-years in its longest dimension. 520 million light-years. Our entire Milky Way, 100,000 light-years across, is to Laniakea what a single atom is to a mountain range. And Laniakea has a center of gravity, a cosmic attractor, a point toward which everything in this enormous structure is gradually, inexorably being pulled. Astronomers call it the Great Attractor. It sits approximately 250 million light-years from Earth in the direction of the constellations Centaurus and Norma. It is a region of space where the gravitational pull is so immense that it is drawing toward it not just our galaxy, not just our local group, not just our Virgo supercluster, but the entire Laniakea supercluster. Everything in this structure, hundreds of thousands of galaxies, is being swept toward this point in space, moving at approximately 600 kilometers per second. And here is the thing that makes the Great Attractor particularly haunting. We cannot see it directly. It sits almost perfectly behind the plane of our own Milky Way from our perspective, obscured by the dust and gas of our own galaxy, a region astronomers call the zone of avoidance. We know it is there because of how it moves everything around it. We know it is there the way you know there is something enormous behind a curtain when you see the curtain bulging toward you. But we cannot see it clearly. It is the universe's great mystery sitting practically in our backyard, a gravitational behemoth that has been pulling at us since before life existed on Earth, and we are only now beginning to understand its true nature. Ask yourself this question right now. If Laniakea, 520 million light-years of galaxies all falling toward a single point, is just one structure among many in the universe, then what does the universe itself look like from far enough away? What would a map of the entire observable universe reveal? The answer, when you first encounter it, is one of the most beautiful and one of the most unsettling things in the whole of human knowledge. The observable universe, the portion of the universe from which light has had time to reach us in the 13.8 billion years since the Big Bang, is approximately 93 billion light-years in diameter. Not because the universe is only 93 billion light-years across, but because space itself has been expanding since the Big Bang, carrying distant galaxies beyond the cosmic horizon even as their light traveled toward us. The universe beyond what we can observe may be vastly, perhaps infinitely, larger. We simply do not know. Within that observable sphere, there are an estimated 2 trillion galaxies. Not 2 trillion stars. 2 trillion galaxies, each containing hundreds of billions of stars. And those galaxies are not distributed randomly. They are organized. They are connected. They form a structure that scientists call the cosmic web. The cosmic web is perhaps the most sublime thing ever discovered. It is the skeleton of the universe itself. It is the architecture of reality. On the very largest scales, the observable universe is not a smooth, uniform distribution of matter. It is a network of vast filaments, threads of galaxies and dark matter stretching for hundreds of millions or even billions of light-years, separated by enormous voids, vast empty bubbles of space where almost nothing exists, some of them hundreds of millions of light-years across. The filaments intersect at nodes where the densest concentrations of galaxies cluster together, and these intersections are among the most dramatic features in all of known existence. Picture a spider's web, but in 3 dimensions, stretched across the sky in every direction, each thread glowing with the light of billions of stars, each junction point blazing with the combined radiance of thousands of galaxies, and between the threads, darkness. Profound, almost perfect darkness. The voids. Empty space on a scale that would take a beam of light hundreds of millions of years to cross. That is the cosmic web. That is what the universe looks like from far enough away. And now we need to talk about the individual features of this web, because they are extraordinary. They are the megastructures of the universe, and each one is more astonishing than the last. Let us begin with galaxy clusters, because they represent the largest gravitationally bound structures in the universe. Structures held together primarily by gravity, as opposed to filaments and superclusters, which are held together partly by gravity and partly by the large-scale flow of matter in the cosmic web. Galaxy clusters are remarkable objects, and the more you learn about them, the stranger they become. The Coma cluster is one of the closest major galaxy clusters to Earth, sitting roughly 320 million light-years away. It contains more than 1,000 galaxies, all bound together by gravity in a region roughly 20 million light-years across. If you could somehow extract yourself from the Milky Way and transport yourself to the Coma cluster, you would find yourself in a very different cosmic environment. One where the night sky, from any planet in any of those 1,000 galaxies, would be filled with the light of neighboring galaxies visible with the naked eye, their spiral arms and elliptical halos painting the darkness in ways we can only dream of from our relatively isolated position in the Milky Way. But the Coma cluster is not just notable for its size or its population of galaxies. It is notable because of something that troubled astronomers for decades, a mystery that fundamentally changed our understanding of the universe and ultimately led to one of the most profound and disturbing discoveries in the history of science. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster when he noticed something deeply wrong. He calculated the mass of the cluster by adding up all the light emitted by its galaxies and converting that to an estimate of how many stars there were and therefore how much mass. Then he calculated how much mass would be needed to keep the galaxies from flying apart, given how fast they were moving relative to each other. And the numbers did not match. By a factor of about 400. The galaxies in the Coma cluster were moving so fast that, if the cluster contained only the mass that Zwicky could see in the form of stars and gas, it should have flown apart long ago. There was not nearly enough visible matter to hold it together. Zwicky concluded that there had to be enormous amounts of invisible matter. Matter that did not emit light, that could not be seen, that could only be detected through its gravitational effects. He called it Dunkel Materie. Dark matter. For decades, Zwicky's idea was largely dismissed or ignored. It seemed too strange, too radical, too much of an ad hoc solution. But then, in the 1970s, an American astronomer named Vera Rubin, working with her colleague Kent Ford, was studying the rotation of galaxies. She was measuring how fast stars at different distances from the center of spiral galaxies were moving, and she found something that should not have been possible. Stars at the outer edges of galaxies were moving just as fast as stars near the center, when by all rights, according to Newtonian gravity and Kepler's laws, they should be moving much more slowly, just as Pluto moves more slowly than Mercury. The rotation curves of galaxies were flat when they should have been declining, and the only explanation was that galaxies were embedded in enormous halos of invisible matter, dark matter, that extended far beyond their visible boundaries and provided the additional gravitational pull needed to explain the motion of their stars. Today, dark matter is one of the most well-established and least understood things in all of physics. We know it exists because of its gravitational effects, on galaxy rotation curves, on the bending of light around galaxy clusters through gravitational lensing, on the large-scale structure of the cosmic web. We know it makes up approximately 27% of the total mass-energy content of the universe, compared to the roughly 5% that is ordinary visible matter, the matter made of protons, neutrons, and electrons that makes up everything you can see, touch, or measure directly. But we do not know what dark matter is made of. It does not interact with light. It does not form stars or planets. It is invisible, indetectable by any direct means we currently possess, and it is everywhere. Right now, as you listen to this, dark matter is passing through your body, through the walls of the building around you, through the earth beneath your feet, at a rate of millions of particles per second. And you feel nothing. It leaves no trace. It interacts with ordinary matter only through gravity, and its individual particles are far too light and numerous to produce any measurable gravitational effect at the scale of a human body. Dark matter is the scaffolding of the universe. It is the invisible skeleton on which the cosmic web is built. Without it, galaxies would not have formed the way they did. clusters would not hold together. The large-scale structure of the universe would be completely different. Dark matter shaped the cosmos we live in, and we still do not know what it is. But dark matter is only half the mystery. The other half is even stranger. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using distant supernovae as standard candles to measure the expansion rate of the universe. They expected to find that the expansion was slowing down, pulled back by the gravity of all the matter in the universe. What they found instead was one of the most shocking results in the history of astronomy. The expansion of the universe is accelerating. It is not slowing down. It is speeding up. Something is pushing space apart, making galaxies recede from each other ever faster with each passing moment. Something is overcoming the gravity of all the matter in the universe and driving the cosmos apart. That something was given the name dark energy, and it is even more mysterious than dark matter. Dark energy makes up approximately 68% of the total mass energy content of the universe. Combined with dark matter's 27%, that means the ordinary matter that makes up everything you have ever seen, touched, thought about, or been, all the stars, all the planets, all the oceans, all the living creatures, all the atoms in every human body that has ever existed, amounts to roughly 5% of everything. We are made of the universe's minority ingredient, the cosmic afterthought, the small print at the bottom of an incomprehensibly vast contract. And the implications of dark energy for the megastructures we are discussing are staggering. Because dark energy operates on the largest scales, the scales of superclusters and filaments and the cosmic web, and it is, over cosmic timescales, winning. The gravitational bonds that hold galaxies together within clusters and superclusters are strong enough to resist dark energy. Those structures will remain bound together for the foreseeable future. But the space between clusters, between superclusters, between filaments, is expanding. The voids are growing. The cosmic web is being stretched. In billions of years, distant galaxies and clusters will recede beyond our cosmic horizon, their light redshifted to invisibility by the expansion of space. The universe will become lonelier and lonelier. The megastructures we can see today will eventually be isolated islands in an expanding ocean of darkness. But before we get to the universe's ultimate fate, we need to stay in the present and explore some of the most dramatic individual megastructures that astronomers have discovered. Objects that push the boundaries of what we thought was possible, that strain our theories, that demand new explanations. Let us talk about galaxy superclusters, and specifically about the structures that go even beyond what we have discussed so far. Because Lania Kea, impressive as it is not the largest structure in the universe. Not even close. Consider the Sloan Great Wall. Discovered in 2003 using data from the Sloan Digital Sky Survey, a massive astronomical mapping project that has cataloged hundreds of millions of galaxies and quasars, the Sloan Great Wall is a filament of galaxies and galaxy clusters stretching approximately 1.4 billion light-years in length. 1.4 billion light-years. If you were to travel along the Sloan Great Wall at the speed of light, the fastest possible speed in the universe, it would take you 1.4 billion years to travel its full length. This is a structure so large that light itself, the fastest thing in existence, would need more time to cross it than the sun has existed. The Sloan Great Wall was, at the time of its discovery, the largest known structure in the universe. And for a while, that record stood. But the universe was not done surprising us. In 2013, a team of astronomers announced the discovery of something called the Hercules Corona Borealis Great Wall. This is a structure so enormous that it does not quite fit comfortably within our existing framework for how large things are allowed to be. The Hercules Corona Borealis Great Wall spans an estimated 10 billion light-years in its longest dimension. 10 billion light-years. The observable universe is 93 billion light-years in diameter. This single structure is more than 10% of the entire observable universe in size. Think about what that means. If you shrunk the observable universe down to the size of a globe, say 1 meter in diameter, The Hercules Corona Borealis Great Wall would be approximately 10 centimeters long. In the scale model of the universe, it would stretch across a significant fraction of the globe. It is not a minor feature. It is not a detail. It is a dominant structure of the universe itself. And this is where things get philosophically troubling in a very specific way. Because one of the foundational assumptions of modern cosmology is the cosmological principle. The idea that, on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means roughly the same everywhere. Isotropic means looking the same in every direction. The cosmological principle is the backbone of our standard model of cosmology. It is the assumption that allows us to use equations derived here on Earth to describe the universe as a whole. But if structures like the Hercules Corona Borealis Great Wall truly exist at the scale that astronomers are claiming, and it is worth noting that there is still some debate about exactly how to define its boundaries and whether it represents a truly coherent structure, then the cosmological principle may be violated. Because a structure 10 billion light-years across is not a local fluctuation. It is not a small departure from homogeneity. It is a fundamental feature of the universe at a scale where, according to our models, everything should be smoothed out and uniform. Some cosmologists argue that the Hercules Corona Borealis Great Wall is the result of a statistical fluctuation or a selection effect in the data, that it may not be as coherent or as large as it appears. Others argue that it represents a genuine challenge to our current understanding of cosmology. The debate is ongoing, and it is one of the most fascinating open questions in the field. Whatever the ultimate answer, the fact that we are even having this conversation, that astronomers have detected something that might be 10 billion light-years long and might challenge the very foundations of our cosmic model, is a testament to how far our understanding has come and how much further it has yet to go. Now let us turn from the largest to the most extreme. Because size alone is not the only measure of a cosmic megastructure's impressiveness. Some structures earn their place in the pantheon of cosmic wonders not by their vast extent but by their sheer violence, their extreme conditions, their role as the universe's most powerful engines of destruction and creation. And no structure embodies this more perfectly than the subject of our next exploration. We need to talk about quasars, and we need to talk about what powers them. A quasar is not a type of galaxy in the traditional sense. A quasar is what happens when a galaxy's central supermassive black hole is actively consuming enormous quantities of material. As gas, dust, and even stars fall into a supermassive black hole, they form an accretion disk, a flattened, rotating structure of matter spiraling inward, heated by friction and compression to temperatures of tens of millions of degrees, radiating energy across the entire electromagnetic spectrum with a power that beggars imagination. The most luminous quasars outshine their entire host galaxies by factors of tens of thousands. A single quasar can emit as much energy as 1 trillion suns. Some quasars produce powerful jets of plasma, relativistic jets, shooting outward from the poles of the black hole at very close to the speed of light, extending for hundreds of thousands or even millions of light-years into the surrounding space. These jets are among the most energetic phenomena in the observable universe. When a relativistic jet from a distant quasar is pointed directly at Earth, we call it a blazar, and the intensity of the radiation reaching us, even from billions of light-years away, can be staggering. The discovery of quasars in the 1960s was one of the most disorienting moments in the history of astronomy. When astronomers first detected these objects, point sources of light that looked like stars but had redshifts indicating they were billions of light-years away, they were deeply confused. Nothing they knew of could produce so much energy from such a compact region. The term quasar is a contraction of quasi-stellar radio source, reflecting the initial puzzlement about their nature. It took years of observation and theorizing before astronomers converged on the explanation we accept today. Supermassive black holes accreting matter at prodigious rates in the early universe. And this brings us to one of the most profound insights of modern astronomy. Quasars are abundant in the distant universe, meaning they were abundant in the early universe, because looking far away means looking back in time, but they are rare nearby. Our Milky Way has a supermassive black hole at its center, a relatively modest one called Sagittarius A star, with a mass of about 4 million solar masses. But it is not currently active as a quasar. The material available to fuel it has largely been consumed or dispersed, and it sits quiet, occasionally flaring to life when a cloud of gas or a star ventures too close. Most large galaxies in the nearby universe are in a similar state. Their central black holes are present but mostly dormant. The age of quasars has largely passed. But in the early universe, in the first billion to 3 billion years after the Big Bang, quasars blazed everywhere. Galaxies were forming, gas was abundant, mergers and interactions between young galaxies were common, feeding their central black holes at extraordinary rates. The early universe was lit up by thousands of quasars, each one shining with the power of 1 trillion suns, each one powered by a supermassive black hole consuming matter at a rate we can barely conceive of. The light from these ancient quasars, having traveled for 10 or 12 or even 13 billion years to reach us, is what we detect when we look at the most distant objects in our sky. And here's a question that should haunt you. If quasars this powerful were common in the early universe, what remnants do they leave behind? What happens to all those supermassive black holes when the fuel runs out? The answer is that they are still there. Every major galaxy in the universe almost certainly contains a supermassive black hole at its center, a monument to the quasar phase it went through in its youth. The centers of galaxies are graveyards of ancient, dormant quasars, black holes that consumed unimaginable quantities of matter in their youth and now sit in the dark, waiting, hidden. The supermassive black hole at the center of the Milky Way, Sagittarius A star, is the closest of these monuments to us, about 26,000 light-years away. In April 2019, a collaboration of radio telescopes spanning the globe, working together as the Event Horizon Telescope, produced the first direct image of a black hole shadow, not Sagittarius A star, but the supermassive black hole at the center of the galaxy M87, a monster with a mass of 6.5 billion solar masses, located about 53 million light-years away. That image, an orange and black ring of glowing gas surrounding a dark central region, was not just a scientific achievement. It was a moment of genuine awe for the entire human species. We had finally seen, with our own instruments, the most extreme object in the universe. A place where the laws of physics as we understand them break down. A place where space and time are so distorted that not even light can escape. Then, in 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A star itself, our own galactic center's black hole, a much smaller and more dynamic target whose turbulent gas environment made imaging it far more challenging. The image was blurry but unmistakable. Another ring of glowing material, another shadow, another confirmation that at the heart of our own galaxy there sits one of these ultimate structures, this endpoint of gravity, this cosmic singularity. But even Sagittarius A star, even the M87 black hole, are relatively modest compared to the true giants. Astronomers have discovered what are called ultramassive black holes with masses exceeding 10 billion solar masses, objects that strain the very mechanisms by which we think black holes form and grow. TUN 618, a quasar located approximately 10.4 billion light-years away in the constellation Canes Venatici, contains a black hole with an estimated mass of 66 billion solar masses. 66 billion times the mass of our Sun. This single black hole contains more mass than many entire galaxy clusters. Its event horizon, the boundary beyond which nothing can escape, has a radius of approximately 195 billion kilometers, roughly 1,300 times the distance from the Earth to the Sun. If you replaced our Sun with TON 618, its event horizon would engulf all 8 planets of our solar system and extend more than 4 times the distance to our outermost planet. TUN 618 is so luminous, so extraordinarily bright, that despite being 10 billion light-years away, it can be detected with moderate-sized telescopes. It is one of the most massive and most luminous known objects in the observable universe. And it almost certainly formed in the first few billion years of cosmic history, meaning that in order to reach 66 billion solar masses so quickly, it must have been consuming matter at a rate that challenges our models of black hole growth. We do not fully understand how black holes this massive formed so early in cosmic history. It is an active area of research, and it is one of those wonderful, uncomfortable places in science where the data is telling us something important and we have not yet figured out exactly what. Now, let us shift our gaze to something different. Something that represents not the endpoint of stars or the engine of quasars, but the aftermath of a different kind of stellar death. One that is quieter in some ways, and in other ways even more extreme. We need to talk about neutron stars and the extraordinary structures they create. When a massive star, one roughly 8 to 20 times the mass of our Sun, reaches the end of its life, it exhausts its nuclear fuel and undergoes a catastrophic collapse. The outer layers of the star rebound off the incredibly dense collapsed core in a titanic explosion called a supernova, one of the most energetic events in the universe, briefly outshining entire galaxies. In the span of seconds, a star that has been burning for millions of years explodes with enough energy to illuminate the cosmos for billions of light years in every direction. And what is left behind, in many cases, is a neutron star. A neutron star is the collapsed remnant of the star's core. Its mass is compressed into a sphere roughly 10 to 20 kilometers in diameter, roughly the size of a city. If you took the entire mass of our Sun and compressed it into a ball the size of a major metropolitan area, you would have something approaching a neutron star's density. A single teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. 1 teaspoon. The density is so extreme that the very electrons and protons in the original stellar core are crushed together, forming neutrons, hence the name. The surface of a neutron star is thought to be a crystalline lattice of nuclei, harder than any material that has ever existed, an outer crust beneath which conditions become increasingly bizarre, perhaps transitioning to exotic states of matter like strange quark matter or color superconducting quark-gluon plasma in the innermost core. Neutron stars are also some of the fastest rotating objects in the universe. When the massive parent star collapses, the conservation of angular momentum causes the rotating core to spin faster and faster as it shrinks, the same principle that causes a spinning ice skater to rotate faster when they pull their arms in. Some neutron stars, called millisecond pulsars, rotate hundreds of times per second. The fastest known pulsar, PSR J1748-2446 AD, rotates at approximately 716 times per second, meaning its surface, at the equator, is moving at roughly 24% of the speed of light. Around and around, 716 times every second, forever. Many neutron stars are pulsars. They emit beams of electromagnetic radiation from their magnetic poles, sweeping through space like cosmic lighthouses. If Earth happens to lie in the path of these beams, we detect a regular pulse of radiation with extraordinary precision, arriving like clockwork. Pulsars are so precisely regular in their timing that they have been used as natural clocks, accurate to a level that rivals atomic clocks on Earth. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University who noticed an anomalously regular radio signal in her telescope data. The signal was so regular, repeating every 1.3373 seconds, that her initial notation in her logbook for it was LGM-1, for Little Green Men. It was serious enough a joke that they actually considered, briefly, that it might be an artificial signal from an extraterrestrial civilization before the natural explanation was determined. But neutron stars, extraordinary as they are, occasionally find companions, other neutron stars, or white dwarf stars, and form binary systems. And when two neutron stars in a binary system spiral together over millions of years, losing orbital energy by radiating gravitational waves, they eventually collide in one of the most violent events in the universe, a kilonova. A kilonova is 1,000 times brighter than a typical nova and is one of the primary sources of heavy elements in the universe. Gold, platinum, uranium, and other R-process elements that cannot be formed in ordinary stellar nucleosynthesis. The gold in every ring on every finger on Earth was forged in the collision of neutron stars. The platinum in every catalytic converter was born in violence, billions of years ago, in some distant galaxy. We are made of dead stars, but we are decorated in the remnants of neutron star collisions. On August 17, 2017, for the first time in history, astronomers detected both gravitational waves and electromagnetic radiation from a single event, the merger of two neutron stars in a galaxy called NGC 4993, located about 130 million light-years from Earth. This event, designated GW 170817, was a landmark in the history of astronomy. It confirmed long-standing theoretical predictions about kilonovae, provided new measurements of the expansion rate of the universe, and inaugurated the era of what astronomers call multi-messenger astronomy, the ability to study cosmic events using multiple different channels of information simultaneously. It was a triumph of human ingenuity and collaboration, involving thousands of scientists and more than 70 space and ground-based observatories around the world. Now let us venture into even more extreme territory. Let us talk about a type of neutron star that pushes even further into the impossible. Let us talk about magnetars. A magnetar is a neutron star with an extraordinarily powerful magnetic field, by far the most powerful magnetic fields known in the universe. The strength of a magnetar's magnetic field is approximately 100 billion times the strength of Earth's magnetic field, and roughly 1,000 times stronger than an ordinary neutron star's field. If a magnetar were located as far away from Earth as the Moon, it would be close enough for its magnetic field to strip the iron from your hemoglobin, the iron in your blood, right out of your body. The mere presence of a magnetar at lunar distance would be lethal to all life on Earth through its electromagnetic effects long before any other mechanism came into play. Magnetars occasionally release what are called giant flares, explosions of electromagnetic radiation so intense that even at cosmic distances, they can be detected. On December 27, 2004, a magnetar called SGR 1806-20, located approximately 50,000 light-years away in our own galaxy, released a giant flare that lasted just 0.2 of a second. In that 0.2 of a second, it released more energy than our Sun emits in 350,000 years. The radiation from this event was so intense that, even at 50,000 light-years distance, it measurably ionized Earth's upper atmosphere. Earth's atmosphere was affected by an explosion 50,000 light-years away. If SGR 1806-20 had been located within a few light-years of Earth, the flare would have triggered a mass extinction event. We were safe only because of the enormous distance. And even then, the universe still managed to leave a mark on our planet. Magnetars are thought to be relatively rare. Only about 30 or so confirmed or candidate magnetars have been identified in our galaxy, but they represent one of the most extreme environments known in the universe. Their surfaces are thought to experience violent, sudden rearrangements of their crystalline crusts, called starquakes, which trigger the emission of powerful radiation. The physics in the interior of a magnetar is so extreme that quantum electrodynamics, the quantum theory of electromagnetic interactions, predicts the vacuum of space itself around a magnetar should become birefringent, meaning that light should travel through it differently in different directions due to the extreme magnetic field. This effect, called vacuum birefringence, was tentatively detected in observations of the neutron star RxJ 1856.5-3754 by a team of astronomers in 2016, providing a remarkable confirmation of quantum electrodynamics in one of the most extreme environments we can access observationally. Let us now turn from the most extreme individual objects to the most extreme large-scale structures, and explore a phenomenon that sits at the intersection of the largest and the most violent. Let us talk about radio galaxies and their jets, and the enormous structures those jets create. When a supermassive black hole at the center of a galaxy is actively feeding, consuming gas and dust and converting it to energy, it often produces enormous relativistic jets of plasma, as we mentioned when discussing quasars. These jets, moving at very close to the speed of light, can travel enormous distances before they slow down and deposit their energy into the surrounding medium. And the structures they create are called radiolobes, enormous bubbles of magnetically confined plasma that glow in radio wavelengths and can span millions of light years. The galaxy Centaurus A, located about 13 million light-years from Earth and one of the closest active galaxies to us, has jets and radiolobes that extend nearly 1 million light-years from its center. Hercules A, a galaxy located about 2 billion light-years away, has radio jets that extend approximately 1.5 million light-years in total. But these are just the nearby examples. Some radio galaxies have jets and lobes that are truly titanic in scale. The radio galaxy 3C 236, located approximately 3 billion light-years away, has radio lobes extending approximately 15 million light-years from one end to the other. 15 million light-years. Remember that the entire Milky Way is 100,000 light-years across. These radio lobes are 150 times larger than our galaxy. They dwarf everything around them. They pump enormous amounts of energy into the intergalactic medium, the thin, hot gas that fills the space between galaxies and clusters, and they have profound effects on the evolution of surrounding galaxies by heating and disrupting the gas that would otherwise collapse to form new stars. This phenomenon, called active galactic nucleus feedback, is one of the most important processes in the life cycles of galaxies. The jets from supermassive black holes do not just affect the immediate vicinity of the black hole. They affect their entire galaxy and the cluster of galaxies around them. They heat the intergalactic medium, suppressing star formation throughout entire galaxy clusters. They shape the evolution of cosmic structures on scales of millions of light-years. A supermassive black hole at the center of a galaxy, through its jets, can literally control the fate of an entire galaxy cluster. The universe's largest structures are shaped by the smallest and densest objects within them. Scale does not matter here. What matters is energy, and black holes are the universe's ultimate energy machines. But speaking of galaxy clusters and the enormous amounts of hot gas that fill them, let us talk about something called the Perseus cluster and about the extraordinary musical note that was discovered emanating from it. The Perseus cluster is a galaxy cluster located about 240 million light-years from Earth. It contains thousands of galaxies and an enormous amount of hot gas, the intracluster medium, heated to temperatures of tens of millions of degrees and glowing brightly in X-rays. The Perseus cluster is one of the brightest X-ray sources in the extragalactic sky, and it has been extensively studied by the Chandra X-ray Observatory since that spacecraft began operations in 1999. In 2003, astronomers studying Chandra observations of the Perseus cluster discovered something extraordinary. There were ripples in the hot gas of the cluster, pressure waves, sound waves, propagating outward from the central galaxy's black hole. The black hole was, in effect, singing. It was producing sound waves, not the kind you can hear, because they are in a medium far too thin to carry sound to our ears and at a frequency far too low for our ears to detect even if it could be carried, but genuine pressure waves nonetheless, with a frequency corresponding to approximately 10 million years per oscillation. This note is approximately 57 octaves below middle C, a full 57 octaves below the lowest note on any piano keyboard. It is the deepest note ever detected in the universe, and it is being played continuously by a supermassive black hole through the hot gas of a galaxy cluster into the fabric of the cosmic structure around it. Think about that image for a moment. The universe is not silent. It is full of sound. Not the sound of explosions or rocket engines. Space has no air for those sounds to travel through. But in the hot plasma of galaxy clusters, there is a medium for sound, and in that medium, the universe is producing music on a scale that makes human music seem like a whisper. The Perseus cluster is reverberating to the bass note of its central black hole, a note that has been playing for billions of years, a sound that will outlast every star currently shining in the observable universe. Now let us take a different direction and explore something that sounds like it belongs in the realm of science fiction but is absolutely, completely real. We are going to talk about Einstein rings and gravitational lensing, and the extraordinary role they play in our understanding of cosmic megastructures. When Albert Einstein published his general theory of relativity in 1915, one of its key predictions was that gravity should bend light. Mass curves spacetime, and light traveling through curved spacetime follows a curved path. Einstein himself calculated that light from a distant star passing close to the Sun should be bent by about 1.75 arcseconds, a tiny but measurable angle. In 1919, during a solar eclipse, British astronomer Arthur Eddington led an expedition to measure this effect. and found that the positions of stars near the edge of the sun's disk were indeed displaced by almost exactly the amount Einstein had predicted. It was a triumph of the new physics, and it made Einstein famous worldwide overnight. But the gravitational deflection of light has implications far beyond testing general relativity. When a massive galaxy or galaxy cluster lies between us and a more distant object, the mass of the intervening structure acts as a gravitational lens, bending and focusing the light from the background object. The result can be spectacular. If the alignment is perfect, the background source, the lensing mass, and our position all in a straight line, the lensed image appears as a complete ring of light surrounding the lens, called an Einstein ring. If the alignment is slightly off, we get multiple images, arcs, or other distorted shapes. Gravitational lensing is not just beautiful. It is enormously powerful as a scientific tool. It allows us to see objects far more distant than we could otherwise observe, because the lens concentrates and amplifies their light. Some of the most distant galaxies ever observed have been detected because they were gravitationally lensed by intervening galaxy clusters. It also allows us to map the distribution of dark matter, because dark matter, despite being invisible, still bends light, and by careful analysis of lensing patterns, astronomers can construct detailed maps of the dark matter distribution in galaxy clusters. This technique has produced some of the most compelling evidence for dark matter's existence and its role in structuring the universe. The Hubble Space Telescope, launched in 1990 and repaired in 1993, has produced some of the most stunning images of gravitational lensing ever obtained. The Hubble Ultra Deep Field images, which reveal thousands of galaxies in a tiny patch of sky no larger than a grain of sand held at arm's length, include many examples of lensed arcs and distorted galaxy images that are among the most beautiful objects in any astronomical photograph. James Webb Space Telescope, launched in December 2021 and beginning full science operations in 2022, has taken this further. With its infrared sensitivity and extraordinary resolution, it has revealed gravitationally lensed galaxies from the first few 100 million years of cosmic history, giving us a window into the universe as it looked in its earliest infancy. One remarkable example of extreme lensing is the object known as the Christmas Tree Galaxy Cluster, or more formally Abell 2744, also called Pandora's Cluster. Located about 3.5 billion light-years away, this cluster has been gravitationally lensed by foreground structures in such a way that some of the background objects it focuses for our inspection are the most distant galaxies ever observed. Pandora's cluster is itself remarkable. It appears to be the result of the simultaneous collision of at least 4 separate galaxy clusters, an event so dramatic and unusual that it has produced complex patterns of dark matter, hot gas, and galaxies that are completely different from what you would expect from a simple collision. It has a dark matter distribution that is displaced from the hot gas of the cluster in ways that have provided some of the strongest direct evidence for the existence of dark matter. The Bullet Cluster is another famous example. Formerly designated 1E0657-558 and located about 3,800,000,000 light-years away. The Bullet Cluster consists of 2 galaxy clusters that have passed through each other. The hot gas of each cluster was slowed by the collision. Gas interacts electromagnetically, so when the 2 gas clouds collided, they decelerated. But the dark matter of each cluster, which does not interact electromagnetically, passed straight through without slowing, separating from the gas. The result is a structure where the hot gas, visible in X-rays, is in a different location from the dark matter, which is mapped by gravitational lensing. The spatial separation between the gas and the dark matter halos is one of the most striking direct pieces of evidence for dark matter ever obtained, essentially ruling out the most popular alternative theories that tried to explain galaxy rotation curves without invoking dark matter. Now, let us venture into territory that is somewhat more speculative, but no less fascinating. We're going to talk about structures that might exist, structures that have been theorized but not yet observed, and structures that might be possible in a universe governed by the physics we think we understand. Ask yourself this: if an advanced civilization, one millions or billions of years more technologically sophisticated than our own, wanted to build something on a cosmic scale, what could they build? What does the universe permit? These are not idle questions. The physicist Freeman Dyson, writing in the 1960s, proposed the concept of a Dyson sphere, a structure built by an advanced civilization around a star to capture all of its energy output. The idea has inspired generations of scientists, engineers, and science fiction writers, and it has actually influenced the search for extraterrestrial intelligence. If such a structure existed, it would transform a star's light output. Instead of visible light, we would see infrared radiation, as the structure converted the star's energy into useful work and radiated the waste heat in longer wavelengths. Astronomers have actually searched for stars showing anomalous infrared excess that might indicate the presence of Dyson spheres or similar megastructures. The most famous recent case was the star KIC 846-2852, also known as Tabby's star, located approximately 1,480 light-years away in the constellation Cygnus. In 2015, citizen scientists analyzing data from the Kepler Space Telescope noticed that this star was dimming in unusual and irregular patterns, sometimes by as much as 22%, which is far too much to be explained by an orbiting planet, and that the dimming events had an irregular, non-periodic pattern unlike anything seen in other stars. The astronomical community became fascinated. Possible explanations ranged from swarms of comets to intrinsic stellar variability to collisions in a debris disk. And yes, some astronomers, including the paper's lead author Tabitha Boyajian, whose name graced the star's nickname, noted that while the most likely explanations were natural, an alien megastructure could not be immediately ruled out. The excitement was enormous. Mainstream media ran headlines about possible alien megastructures. The SETI Institute trained its Allen telescope array on Tabby's star looking for radio signals. And the result? No artificial signals were detected. Over subsequent years, more observations were made, and the evidence increasingly pointed toward a natural explanation involving a circumstellar dust cloud, perhaps the remnants of a disrupted planetary body or a swarm of comets, periodically transiting the star and dimming its light. By 2018, the dust explanation was widely accepted as the most likely answer, though the exact nature of the event remains somewhat uncertain. Tabby's star is a good example of how extraordinary claims require extraordinary evidence, and of how exciting, productive, and ultimately responsible science can be even when the final answer is less dramatic than the initial speculation. But the idea of megastructures built by civilizations, while firmly in the realm of speculation when it comes to actual detection, is not unscientific. It is a serious area of inquiry within the SETI community, and it has led to fascinating theoretical work about what kinds of structures physics actually permits. A civilization that could harvest the energy of an entire star. A civilization that could build structures spanning the distance between stars. A civilization that could, in principle, manipulate the orbit of stars themselves, rearranging them to serve purposes we can only imagine. These are not fantasy. They are extrapolations of physics. What happens when you take known physical principles and extend them to the limit of what is possible? The physicist Nikolai Kardashev proposed in 1964 a classification system for civilizations based on their energy use. A Type 1 civilization harnesses all the energy available on its planet. A Type 2 civilization harnesses all the energy of its star. A Type 3 civilization harnesses all the energy of its galaxy. We are currently somewhere between Type 0 and Type 1. We have not yet mastered all of Earth's energy resources, let alone anything beyond. The leap from Type 1 to Type 2 to Type 3 represents not just an engineering challenge, but a change in the kind of structures that could be built. A Type 3 civilization, building structures on galactic scales, would produce megastructures that would be detectable from other galaxies. If such civilizations existed and had existed long enough to build on these scales, we might be able to see them. The fact that we have not, that the universe appears, as far as we can tell, to be empty of such civilizations, is itself a profound and troubling fact, a manifestation of what is called the Fermi paradox. Enrico Fermi, the physicist and architect of the first nuclear reactor, is said to have asked over lunch one day in 1950, "Where is everybody?" Given the age of the universe, given the number of stars, given the number of potentially habitable planets, Given the possibility that life and intelligence might arise on a fraction of them and then expand and develop over millions and billions of years, where are all the alien civilizations? Why is the universe not full of evidence of their existence? The silence is one of the great puzzles of our time. Some theorists suggest that the absence of evidence for megastructures is itself a clue that either civilizations do not survive long enough to build them, or that there is some other factor, perhaps called the Great Filter, that prevents civilizations from reaching the level of technological development needed. Others suggest that perhaps advanced civilizations choose not to build in ways we could detect, or that our search methods are simply not yet sensitive enough. The debate is rich and unresolved, and every advance in our astronomical instruments adds new data points to it. But let us return to what we know is out there. Because the natural universe, without any help from hypothetical alien engineers, has produced structures that are every bit as dramatic and awe-inspiring as anything a civilization could build. Let us talk about cosmic voids, the vast empty spaces that are as important as the structures within the cosmic web. A cosmic void is a region of the universe largely devoid of galaxies. Not completely empty. There are still some galaxies within voids, just far fewer than in the surrounding filaments and walls, but dramatically underdense compared to the cosmic average. Voids are everywhere in the universe, separated by the filaments and walls of the cosmic web, and they occupy the majority of the universe's volume. The largest void yet identified is called the VOID void, discovered in 1981 when a survey found a sphere of space roughly 330 million light-years in diameter that was almost completely empty of galaxies. 330 million light-years. A sphere of near-nothingness larger than many galaxy superclusters, larger than the distance light has traveled since before the earliest complex life on Earth. Inside the VOID void, the density of galaxies is roughly 1/10 of what would be expected for that volume of space. It is not completely empty. About 60 galaxies have been found within it, but it is so dramatically underdense that it stands out as one of the most striking features of the large-scale structure of the universe. When the VOID void was first discovered, astronomer Robert Kirshner reportedly said, "We do not know whether to believe our own results." The void was so large that some astronomers initially suspected it might be an artifact of the survey methodology. But subsequent observations confirmed it. It is real. And it is not unique. The universe contains many large voids, and they have played an important role in shaping cosmic structure. Voids push matter outward along their boundaries, contributing to the cosmic web by concentrating matter into the filaments and walls that separate them. But there is an even larger void that has attracted attention in recent years, though calling it a void is somewhat of an oversimplification. The cold spot is a region in the cosmic microwave background radiation, that faint glow of the universe's earliest light that fills the sky in every direction, that is significantly cooler than the surrounding CMB. It was discovered in 2004 in data from the WMAP satellite. The cold spot subtends an angle of about 5 degrees on the sky and is about 150 microkelvin cooler than the average CMB temperature. Which might not sound like much, but in the context of the extraordinarily uniform CMB, it is a major anomaly. Various explanations have been proposed for the cold spot. One possibility is that it is simply a statistical fluctuation, that in a universe as large as ours, such cold regions are not impossible, just unlikely, and we happen to find ourselves in the right position to observe one. Another possibility, which generated significant excitement when it was proposed, is that the cold spot is the signature of a large void in the matter distribution along the line of sight. A supervoid so large that photons of CMB radiation lost energy as they climbed out of the void's gravitational potential well, arriving at our detectors slightly cooled. In 2015, a team of astronomers using data from the BOSS survey reported finding what they described as a supervoid about 1.8 billion light-years in size at about 3 billion light-years distance in approximately the right direction to explain the cold spot. If confirmed, this would make it the largest structure in the known universe. But the controversy does not end there. Because another explanation for the cold spot, one that is firmly in the realm of speculation but has garnered serious attention from cosmologists, is that it might be the imprint of a collision between our universe and a neighboring universe in a multiverse. If the universe we inhabit is one of many, If inflation, the rapid expansion of space in the universe's first moments, created a vast collection of bubble universes, each with potentially different physical constants and properties, then collisions between these bubbles, occurring at the boundaries where they first came into contact, should leave signatures in the CMB. The cold spot's unusual shape and temperature profile have been proposed as potential evidence for such a collision. This is, to be very clear, a speculative theory. The multiverse is a hypothesis that is extremely difficult to test observationally, by its very nature. But the fact that serious cosmologists are examining the cold spot as a potential window into physics beyond our universe is a testament to how far our ambitions and our observations have reached. We are no longer simply mapping the structures within our observable universe. We are looking for signatures of whatever might lie beyond it. Now let us talk about one of the most dramatic single events in the life cycle of cosmic megastructures. We have talked about how stars are born, how they live, how they die in supernovae, and how they leave behind neutron stars and black holes. But we have not yet talked about the most dramatic stellar death of all. One that is not triggered by the exhaustion of nuclear fuel, but by a catastrophic external event. We need to talk about gamma-ray bursts. A gamma-ray burst, or GRB, is the most energetic explosion known in the universe after the Big Bang itself. They occur, on average, about once per day somewhere in the observable universe, and they release more energy in a few seconds to minutes than our Sun will emit over its entire 10 billion year lifetime. In their brief duration, they briefly outshine the entire observable universe in gamma rays. Gamma-ray bursts come in two varieties. Short gamma-ray bursts, lasting less than 2 seconds, are now understood to be produced by the merger of two neutron stars or a neutron star and a black hole, the same type of cataclysmic collision that produces kilonovae. Long gamma-ray bursts, lasting more than 2 seconds and sometimes for several minutes or more, are associated with a special type of core-collapse supernova called a hypernova, in which the collapsing stellar core forms a rapidly rotating black hole that drives powerful jets of material along the rotation axis at very close to the speed of light. These jets, punching through the outer layers of the dying star and then into the surrounding medium, produce the intense burst of gamma rays we detect from Earth. The nearest gamma-ray burst ever detected that posed a potential threat to Earth occurred about 2 billion years ago and was fortunately not pointed at us. If a long gamma-ray burst were to go off within a few thousand light years of Earth and the jet were aimed in our direction, the effects would be catastrophic. The gamma radiation would destroy the ozone layer on the hemisphere of Earth facing the burst, exposing the surface to intense ultraviolet radiation from the Sun. Some scientists have proposed that the Ordovician mass extinction event, which occurred approximately 440 million years ago and wiped out roughly 85% of all marine species, may have been caused by a nearby gamma-ray burst. This remains speculative. The Ordovician extinction's causes are still debated, but it is a chilling possibility, a reminder that the universe's most extreme events can reach across thousands of light years and reshape the course of life on a planet. The study of gamma-ray bursts has given astronomers a powerful tool for probing the universe at extreme distances. Because they are so luminous, gamma-ray bursts can be detected at enormous distances. The most distant gamma-ray burst ever detected, GRB 090423, occurred at a redshift of approximately 8.2, meaning it took place about 13.1 billion years ago, just 630 million years after the Big Bang. The light from this explosion, born in the first chapter of cosmic history, only reached Earth in 2009. It traveled for more than 13 billion years to reach us, a message from the universe's infancy written in gamma rays and decoded by orbiting telescopes. Now, let us explore one of the most mind-bending aspects of cosmic megastructures: the role of gravity waves, or rather, gravitational waves, in both creating and connecting the structures we have been describing. Albert Einstein predicted the existence of gravitational waves in 1916 as a consequence of his general theory of relativity. According to general relativity, any massive object that accelerates, changes its velocity, distorts space-time in a way that propagates outward as a wave at the speed of light. Two stars orbiting each other, for example, produce gravitational waves. Two black holes spiraling together and merging produce enormous gravitational waves. And these waves, unlike light or radio waves, cannot be absorbed or scattered by intervening matter. They pass through everything. They distort space itself. The problem is that gravitational waves are extraordinarily faint. By the time they reach Earth from any astrophysical source, the distortion of space they cause is almost unimaginably tiny. The first direct detection of gravitational waves, on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a distortion of space with an amplitude of about 1/10,000th the size of a proton. The mirrors of the LIGO detector, separated by 4 kilometers, moved relative to each other by a distance 1,000 times smaller than the width of a proton. And we detected it. It was one of the greatest experimental achievements in the history of science. That first detection was the merger of 2 black holes, each roughly 30 solar masses, located approximately 1,400,000,000 light-years away. The black holes spiral together over millions of years, losing energy to gravitational radiation, their orbits shrinking as they accelerated toward the final plunge. In the last fractions of a second before the merger, they were releasing more power in gravitational waves than all the stars in the observable universe combined release in electromagnetic radiation. And that final chirp, a fraction of a second of gravitational wave signal, was what LIGO detected. Since that first detection in 2015, LIGO and its partner observatory Virgo have detected dozens more gravitational wave events, merging black holes, merging neutron stars, and potentially merging systems involving black holes and neutron stars. Each detection is a window into the most extreme environments in the universe, a direct measurement of the curvature of space-time produced by some of the most dramatic events in cosmic history. And each detection is made possible by instruments of almost supernatural sensitivity, built by thousands of scientists and engineers working for decades. In the future, planned space-based gravitational wave detectors like the Laser Interferometer Space Antenna, LISA, which is scheduled to launch in the mid-2030s, will detect gravitational waves at much lower frequencies than LIGO can access. These lower frequency waves are produced by the mergers of supermassive black holes, the same kind that power quasars and that sit at the centers of galaxies. When 2 massive galaxies merge and their central black holes eventually spiral together, they will produce a gravitational wave signal of staggering power. LISA will be able to detect these mergers throughout the observable universe, giving us a completely new way to observe the largest and most dramatic events in the lives of galaxies and galaxy clusters. And there is yet another window into low-frequency gravitational waves that has recently opened. It is called the Pulsar Timing Array, and it is one of the most elegant scientific instruments ever conceived. Millisecond pulsars, those extraordinarily precise cosmic clocks that rotate hundreds of times per second, can be used as a detector for gravitational waves. A gravitational wave passing through the Milky Way would slightly alter the timing of pulses arriving at Earth from different pulsars in slightly different ways, depending on the relative orientation of each pulsar and the passing wave. By monitoring dozens of pulsars simultaneously over years and decades, astronomers can effectively use the entire Milky Way as a gravitational wave detector. In 2023, multiple independent pulsar timing array collaborations in North America, Europe, China, India, and Australia announced evidence for what they call the gravitational wave background. This is a stochastic background of gravitational waves, analogous to the cosmic microwave background of electromagnetic radiation. A sea of overlapping gravitational waves from the mergers of countless supermassive black holes throughout cosmic history, arriving from all directions simultaneously and producing a constant, low-level vibration in spacetime. The detection was not yet at the level of certainty required to call it a definitive discovery, but the evidence was consistent and compelling across independent collaborations using different methods, and it was described as a landmark moment in gravitational wave astronomy. If confirmed, the gravitational wave background will provide an entirely new way to study the history of galaxy mergers and supermassive black hole growth throughout cosmic time. It will tell us things about the largest structures in the universe, the merging of galaxy clusters, the formation of the largest black holes, that we cannot access through any other means. We are opening yet another eye on the cosmos, and each new eye reveals something astonishing that the others had missed. Now let us turn to something that is, in some ways, the ultimate megastructure. Something that is not just large in 3 dimensions of space, but extends across the 4th dimension, time, in a way that makes it a structure of a completely different kind. We are going to talk about the cosmic microwave background radiation as a megastructure. The CMB is the oldest light in the observable universe. It was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons, particles of light, to travel freely for the first time. Before this moment, the universe was opaque. The hot plasma of the early universe scattered light in all directions, preventing it from traveling far. When the universe became transparent, a flash of light was released that has been traveling ever since, filling all of space, and that we detect today as a faint glow of microwave radiation coming equally from all directions. The CMB has a temperature of approximately 2.7 Kelvin, just 2.7 degrees above absolute zero. It is the coldest and oldest electromagnetic radiation in the universe, and it is exquisitely uniform. The temperature differences between different parts of the CMB sky are only about 1 part in 100,000, tiny fluctuations in a sea of near-perfect uniformity. These tiny fluctuations, though, are of immense importance. They are the seeds of all the structure we have been discussing. The density variations in the early universe that were amplified by gravity over billions of years to become galaxies, galaxy clusters, superclusters, and the cosmic web. The CMB is, in a sense, a snapshot of the universe at the age of 380,000 years. When you look at the CMB, you are literally looking at an image of the early universe, a spherical shell of ancient light surrounding us in all directions, each photon having traveled for almost 14 billion years to reach your eyes. The CMB is the universe's baby picture, and everything we see in it, every galaxy, every star, every living creature, every thought that has ever been thought, grew from the tiny wrinkles visible in that ancient glow. The study of the CMB has been one of the most productive endeavors in the history of cosmology. It has given us precise measurements of the age of the universe, the composition of the universe, the relative fractions of ordinary matter, and dark energy, the geometry of the universe, which appears to be flat, meaning the large-scale curvature of spacetime sums to zero, and the seeds of cosmic structure. Every major CMB experiment, from the first satellite measurements in the early 1990s by the COPE satellite, to the WMAP satellite in the 2000s, to the Planck satellite which concluded its science mission in 2018, has refined our picture of the early universe and our standard cosmological model with ever-increasing precision. And yet the CMB still holds mysteries. The cold spot we discussed earlier, a subtle alignment of the largest scale features of the CMB that some astronomers have found puzzling, an alignment that seems to point in a particular direction in the sky, a direction that has been called the axis of evil by some cosmologists, not because of any actual malevolence, but because it seems to single out a preferred direction in what should be a perfectly isotropic universe. Whether this alignment is a genuine cosmological signal or a statistical artifact is still debated. But it is another thread of tension in the otherwise remarkably successful standard model of cosmology, another hint that perhaps we do not yet have the complete picture. Let us now venture into one of the most dramatic frontiers of observational astronomy, the first light in the universe. Not the CMB, which is the light released at recombination, but the very first stars and galaxies formed in the universe's first few 100 million years. This epoch is called the Epoch of Reionization, and studying it is one of the primary goals of the James Webb Space Telescope. After the CMB was released, the universe entered a period called the Cosmic Dark Ages. There were no stars, no galaxies, just hydrogen and helium gas, cooling and slowly clumping under gravity, dark matter halos forming and gathering the first clouds of gas. Then, somewhere around 100 to 200 million years after the Big Bang, the first stars ignited. These were population 3 stars, a hypothetical class of stars that has never been directly observed, but whose existence is strongly predicted by theory. Population 3 stars formed from gas that contained only hydrogen and helium, with no heavier elements, because heavier elements had not yet been synthesized in any stellar furnaces. Models predict that population 3 stars were extremely massive, perhaps tens or hundreds of times the mass of the Sun, and extremely luminous and hot. Their lives would have been brief. Massive stars burned through their fuel quickly, and their deaths would have been spectacular, enriching the surrounding gas with the first heavy elements produced in their cores and by their supernova explosions. The radiation from the first stars and galaxies gradually reionized the neutral hydrogen gas of the universe, breaking apart the hydrogen atoms back into protons and electrons, ending the cosmic dark ages and beginning the universe we live in today, where the intergalactic medium is an ionized plasma through which light can travel freely. Understanding this transition, this era when the universe was lit up for the first time by its first generation of stars and galaxies, is one of the holy grails of modern observational astronomy. The James Webb Space Telescope was designed in part specifically to peer into this era. With its large mirror, exquisite sensitivity, and infrared capability. Infrared because the light from these distant, early galaxies is redshifted to infrared wavelengths by the expansion of the universe. JWST has already begun to reveal galaxies from the first few 100 million years of cosmic history in extraordinary detail. Some of its early results have been genuinely surprising, revealing galaxies that appear more massive and more evolved than our models predicted for such an early cosmic epoch. These results are challenging and refining our understanding of how galaxies form and grow. One specific result that generated enormous excitement in the astronomical community in 2023 involved the discovery of what appear to be massive, well-formed galaxies at redshifts corresponding to the first 500 million years after the Big Bang. These galaxies were more massive, more numerous, and more structured than the theoretical models of galaxy formation predicted. Some researchers describe them as too big too soon. Galaxies that should not have been able to assemble so much mass in such a short time given our current understanding of how galaxies form. The results were reported by teams using JWST data and were reported in high-profile journals, sparking intense debate and discussion in the astronomical community. Some experts cautioned that the mass estimates were uncertain and that additional observations and analysis were needed before drawing firm conclusions. Others argued that the results, if confirmed, would require revision of our models of early galaxy formation, possibly involving new physics, more efficient star formation than our models predict, or new mechanisms of rapid gas accretion. The debate is ongoing and active, and it represents science at its best. Extraordinary data meeting theoretical predictions and sparking revision, refinement, and new understanding. Now let us explore one more category of cosmic megastructure before we begin our journey toward the largest scales of all. Let us talk about nebulae, the nurseries where stars are born, and the monuments that dying stars leave behind. A nebula is a cloud of gas and dust in space. The word comes from the Latin for cloud or mist. There are several different types of nebulae, and each represents a different phase in the cycle of stellar birth, life, and death. Emission nebulae are clouds of gas that have been ionized by the ultraviolet radiation of nearby hot, young stars, causing them to glow with characteristic colors: the red of hydrogen alpha emission, the blue-green of oxygen doubly ionized, the blue of nitrogen. Reflection nebulae are clouds of dust that reflect the light of nearby stars without ionizing, producing a cool blue glow. Dark nebulae are clouds of gas and dust so dense that they block the light of more distant stars and nebulae, appearing as dark patches against bright backgrounds. The most famous nebula in the sky is almost certainly the Orion Nebula, visible to the naked eye in the sword of the constellation Orion as a faint fuzzy patch. In reality, it is a stellar nursery located about 1,344 light-years from Earth, roughly 24 light-years across, and containing hundreds of young stars in the process of forming. It is one of the closest and most intensely studied star-forming regions in our galaxy, and it is a spectacular object in telescopes of any size. But planetary nebulae, a somewhat misleading name, since they have nothing to do with planets, are even more dramatic. When a star like our Sun reaches the end of its life, after exhausting its nuclear fuel and swelling into a red giant, it sheds its outer layers in a slow wind that expands outward into space. The remaining hot stellar core, a white dwarf, radiates intense ultraviolet light that illuminates the ejected gas, causing it to glow in beautiful, complex, often symmetric patterns. the Ring Nebula in Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco. These are all planetary nebulae, the ghostly remnants of dead stars, each one unique in shape and color, each one a monument to a star that burned for billions of years and then gently dispersed into the cosmos, seeding the interstellar medium with the heavy elements it synthesized in its core. And then there are supernova remnants, the aftermath of massive stellar deaths. The Crab Nebula in Taurus is the remnant of a supernova observed by Chinese and Arab astronomers in 1054 AD, a star that became so bright it was visible in daylight for weeks. Almost 1,000 years later, the expanding shell of gas from that explosion spans about 11 light-years and contains at its center the Crab Pulsar, a neutron star rotating 30 times per second, powering the entire nebula with its emission of energetic particles. The Crab Nebula is one of the most intensely studied objects in the sky, a laboratory for understanding the physics of supernova remnants, neutron stars, and the interaction of relativistic particles with magnetic fields. The Cygnus Loop, also called the Veil Nebula, is a much older supernova remnant, the remnant of a star that exploded approximately 8,000 years ago. It spans about 3 degrees on the sky, about 6 times the diameter of the full moon, and is a complex, filamentary structure of glowing gas, shock-heated by the expanding blast wave of the original explosion, still expanding into the surrounding interstellar medium thousands of years later. The original supernova would have been visible to our ancestors with the naked eye, a new star in the sky brighter than any other, though no historical record of it survives. Cassiopeia A is a supernova remnant where the original explosion is estimated to have occurred roughly 340 years ago, though no clear historical record of anyone observing the star's explosion has been found. Perhaps it was obscured by dust. It is one of the brightest radio sources in the sky, a rapidly expanding shell of gas moving at about 6,000 kilometers per second, heated to millions of degrees, embedded in a cloud of material ejected by the star in the centuries before the explosion. At its center sits a neutron star, the Cassiopeia, a compact central object, still hot from the explosion, cooling slowly, a relic of one of the most violent events in our cosmic neighborhood in recorded history. These nebulae, these stellar nurseries and stellar monuments, are not just beautiful. They are the factories and recycling plants of the galaxy. They take the heavy elements synthesized in stellar cores and dispersed by stellar winds and supernova explosions, and they incorporate them into the next generation of stars and planets. The oxygen you are breathing right now was forged in the nuclear furnace of a long-dead star and dispersed into the interstellar medium by that star's death, to be gathered up in the cloud of gas and dust from which our solar system formed 4.6 billion years ago. We are not just made of stardust in a poetic sense. We are literally, chemically, physically made of the material that was once inside other stars. Stars that lived and died before our sun was born, in places we cannot identify, in events we were not there to witness. The universe is its own recycling system, its own closed loop, turning death into life and life into death in an endless cosmic cycle. Now let us journey to the very edge of our knowledge, and beyond. We have talked about the cosmic web, about superclusters and voids, about the CMB and gravitational waves. Now let us confront the most profound question of all. What is the fate of the universe? What will happen to all these magnificent megastructures, the galaxies, the clusters, the filaments, the web itself, over the next trillions of years? The current best evidence suggests that we live in a universe dominated by dark energy, a form of energy that fills all of space and drives accelerating expansion. If dark energy remains constant over time, as the simplest model suggests, then the universe will continue to expand forever at an accelerating rate. The consequences, played out over cosmic time, are both beautiful and melancholy. In approximately 4 to 5 billion years, the Andromeda Galaxy will collide with the Milky Way, as we have already discussed. The merger will take place over billions of years, and the resulting galaxy, Milkomeda, will be a large, unstructured elliptical galaxy, its spiral arms and disk structure gone, replaced by a more diffuse swarm of stars. By this time, our sun will have been evolving for another 4 to 5 billion years and will be swelling into a red giant, its outer layers engulfing the inner planets. Earth, if it still exists in any recognizable form, will be unrecognizably different. Scorched, perhaps swallowed, its oceans long since evaporated. Whatever life might exist in our solar system at that time will have had to migrate outward, to the moons of the outer planets or beyond. In 100 billion years, the acceleration of the universe's expansion will have carried all galaxies beyond the local group beyond our cosmic horizon. They will be receding faster than light can cross the expanding space between us, making them permanently unobservable. The night sky, from any world that might exist in the Milkomeda galaxy at that time, will contain only the stars of that single merged galaxy and perhaps a handful of nearby dwarf galaxies still gravitationally bound within the local group. The rest of the universe, the trillions of galaxies we can see today, will have vanished beyond a veil of expanding darkness. Future astronomers, if they exist, will see a universe far smaller and far lonelier than the one we observe today. They might have no way of knowing about the vast cosmic web, the superclusters, the filaments, all of it hidden forever by the expansion of space. In 10 trillion years, 10,000 billion years, the era of star formation will draw to a close. Most of the gas in galaxies will have been consumed, converted into stars over the long ages since the Big Bang. The last of the small red dwarf stars, which burn their fuel so slowly they can live for trillions of years, will still be shining, dim and red, in the slowly cooling remnants of galaxies. The universe will be aging, its stellar population growing sparser and dimmer. Giant, old white dwarfs will be cooling. Neutron stars will be slowly losing their heat and becoming cold, dark spheres. Black holes, stellar mass and supermassive alike, will still be there, invisible, inert, patient. Eventually, in a very distant future, so distant it makes even the life of a red dwarf star seem brief, even the white dwarfs will cool to black dwarfs, cold dead remnants of former stars, invisible in the dark. The universe will be a black, cold, nearly empty place, filled with dark objects and flooded with the ever-cooling glow of CMB radiation, by then reduced to temperatures of mere billionths of a Kelvin. And then, in the incomprehensibly remote future, timescales written with numbers that have so many zeros they cannot be comfortably expressed in ordinary notation, quantum mechanics predicts that even the most stable nuclei will eventually decay, given enough time. Even protons, the fundamental building blocks of ordinary matter, may eventually decay, though this prediction depends on specific theories of particle physics that have not been confirmed experimentally. If protons do decay, then all the matter that has ever existed, every neutron star, every cold white dwarf, every planet, every molecule, will eventually dissolve into a thin gas of elementary particles, photons, and energy. The black dwarfs will evaporate. The neutron stars will dissolve. Nothing will be left but black holes and the lightest elementary particles. And even black holes are not eternal. Stephen Hawking showed in 1974 that black holes should very slowly lose mass through a quantum mechanical process, now called Hawking radiation, in which pairs of virtual particles are produced near the event horizon, one falling in and one escaping, over an extraordinarily long time, far longer than the current age of the universe. A black hole of stellar mass will evaporate completely, radiating away its entire mass as Hawking radiation. A supermassive black hole like the one at the center of M87, with 6.5 billion solar masses, would take approximately 10 to the power of 100 years to evaporate by Hawking radiation. A number so large it cannot be meaningfully compared to anything we know. And when it finally does evaporate, there will be nothing left, just the faintest whisper of radiation, spreading out across a cold, dark, empty cosmos. This is the heat death of the universe. The ultimate fate, as far as we can currently project. Not a bang, not an explosion, just a slow, patient, irresistible cooling and thinning and darkening, until everything that ever was is gone, and the universe is a vast, cold, empty space of maximum entropy, with no structure, no energy gradients, no possibility of any work being done, no possibility of life or thought or beauty or pain or anything at all. It is, depending on your perspective, either the saddest thing imaginable or something profoundly, strangely beautiful. The universe had its moment of glory, Its 13.8 billion-year explosion of creativity and complexity in structure, and it will have an ending, long and cold and quiet, after which there will be nothing left to mourn what was lost. We exist in the brief, brilliant flowering of the universe's middle age, after the chaos of its birth, before the silence of its death. We are living in the golden age of the cosmos, and we do not always appreciate how lucky that makes us. But now, before we reach those cold and distant ages, let us come back to the present, and to one more astonishing feature of the universe that we have saved for last. We need to talk about the cosmic web's most spectacular intersection points. We need to talk about what happens when not two, not three, but dozens of galaxy clusters fall together in a single, cataclysmic collision. We need to talk about the El Gordo cluster. El Gordo, a Spanish nickname meaning the Fat One, is formally designated ACTCL J0102-4915. It is a massive galaxy cluster located approximately 7 billion light-years from Earth. When it was first identified in 2011 using data from the Atacama Cosmology Telescope and subsequently confirmed and studied using the Hubble Space Telescope, Chandra X-ray Observatory, and the Very Large Telescope in Chile, it astonished the astronomical community. El Gordo is the most massive, hottest, and most luminous galaxy cluster ever observed at its distance in the universe. Its total mass is estimated at about 2 quadrillion, 2 million billion, solar masses. It is so massive that it presents a significant challenge to cosmological models. It is more massive than our current understanding of structure formation predicts should be possible for a cluster at that distance and epoch. Some researchers have argued that its existence, combined with a few other extreme clusters, implies that either our cosmological model needs revision or that these clusters have been somehow overestimated in mass. El Gordo appears to be the result of the high-speed collision of two massive galaxy clusters, similar to the Bullet cluster but on a far larger scale. The hot gas from the two clusters has been shocked and distorted by the collision, producing a bullet-like or comet-like shape visible in X-rays. The collision speed has been estimated at over 2,000 kilometers per second, roughly 2 million miles per hour. Two enormous collections of thousands of galaxies and trillions of stars, smashing into each other at 7,200,000 kilometers per hour. The collision has been ongoing for hundreds of millions of years and will continue for billions more before the two clusters merge into a single, even more massive structure. Hubble Space Telescope observations of El Gordo have revealed a striking gravitational lensing effect. The cluster's immense mass bends and distorts the light of background galaxies into arcs and rings visible in the images, providing a map of its dark matter distribution and confirming that, like the Bullet cluster, the dark matter of the two merging clusters is separated from the hot gas. The cluster's image, released in various forms over the years of study, is one of the most dramatic astronomical images ever produced. A vast, glowing cloud of hot gas trailing behind the two colliding galaxy concentrations, surrounded by the ghostly arcs and rings of gravitationally lensed background galaxies. El Gordo is a reminder that the universe is not a static, peaceful place. On every scale, from the subatomic to the cosmological, the universe is in motion, changing, colliding, growing, dying. The cosmic web is not a fixed structure but a dynamic, evolving network, constantly being shaped by gravity, dark energy, and the countless collisions and mergers that have been taking place since the first structures formed. We are frozen in a single frame of a 13.8 billion-year movie, and the frames before and after us contain events of breathtaking violence and beauty. And if you think El Gordo is dramatic, consider what the universe is doing right now, today, in our cosmic backyard. The Great Virgo cluster, with its 1,300-plus galaxies, is pulling everything in the local supercluster toward it. The Milky Way and the local group are flowing toward the Great Attractor. Perseus Pisces, another massive supercluster, is pulling matter in the opposite direction. The cosmic web is literally flowing. Matter streaming along filaments, falling into clusters, with everything in the supercluster scale being assembled in real time. We are not spectators of a completed universe. We are participants in an ongoing process of cosmic construction, and the blueprint is still being drawn. Now let us ask ourselves the question that underlies everything we have discussed. Why does the universe make these structures? Why does it build things at all? Why, instead of just a uniform gas of hydrogen and helium cooling and expanding forever, did the universe end up with galaxies and stars and planets and people? The answer has two parts. The first is gravity. Gravity is the great organizer. Given any small initial fluctuation in the density of matter, any region that is even slightly denser than its surroundings, gravity will amplify that fluctuation over time. The slightly denser region attracts material from its surroundings, becoming denser still, attracting even more material. The process is self-reinforcing, and given enough time, even a tiny initial fluctuation can grow into a galaxy cluster, a filament of the cosmic web. The initial fluctuations, those tiny temperature variations in the CMB, were probably produced during inflation, the period of extremely rapid cosmic expansion in the universe's first fraction of a second. Inflation stretched quantum fluctuations, inherent quantum uncertainty in the density of matter, to cosmological scales, seeding the universe with the initial non-uniformities that gravity could then amplify over billions of years. The second part of the answer is more subtle and more profound. It involves the second law of thermodynamics, the principle that entropy, or disorder, always tends to increase in a closed system. How can the universe, which should be tending toward greater disorder, produce the extraordinary order and complexity of galaxies and stars and planets and life? The answer is that the universe exploits energy gradients, differences in energy density between regions of space, to produce local pockets of order at the expense of greater disorder elsewhere. Stars radiate their energy into space, into a cold, dark vacuum. In doing so, they produce entropy far faster than they produce order. But in the process, a tiny fraction of their energy output falls on planets, where it drives extraordinarily complex chemical and biological processes. Life is not a violation of the second law. Life is an extraordinarily sophisticated mechanism for increasing entropy, just in a roundabout way. The universe builds complex structures precisely because doing so allows it to increase overall disorder more efficiently. This perspective, that the universe's megastructures and the life that arises within them are all part of the universe's process of maximizing entropy, is one of the most profound and humbling insights in all of science. We are not accidents. We are not unimportant. We are, in a very real sense, the universe's way of understanding itself and of fulfilling its deepest thermodynamic imperatives. We are the universe looking at itself, marveling at its own complexity, asking the questions it has been building towards since the first moment of creation. Consider this question and sit with it for a moment. If you could travel instantaneously to any point in the observable universe, to the heart of the Coma cluster, or the center of a galaxy in the Sloan Great Wall, or a planet orbiting a star in the Perseus cluster, what would you find? Would there be observers there, looking up at their own sky, wondering about the structures they inhabit? Would there be beings who have mapped their own cosmic web and discovered that they, too, are a tiny ripple in an ocean of incomprehensible vastness? Or would those places be empty, beautiful, magnificent, vast, and silent? We do not know. The universe does not tell us. The Fermi paradox hangs over every question about life and intelligence beyond Earth, unanswered and haunting. We know that the universe is capable of producing life. It produced us, after all, which establishes that the process is at least physically possible. We know that the ingredients are widespread. Carbon, hydrogen, oxygen, nitrogen, the building blocks of chemistry and life, are among the most common elements in the universe, produced in stars and dispersed by supernova explosions throughout galaxies everywhere. We know that planets are common, extraordinarily common, in fact. Data from the Kepler Space Telescope and subsequent planet-hunting missions have revealed that virtually every star in the Milky Way has planets, and that planets in the habitable zone of their stars, not too hot, not too cold for liquid water, are extraordinarily numerous. The Milky Way alone may contain billions of potentially habitable planets, and there are 2 trillion galaxies in the observable universe. The possibility that life is common in the universe is taken seriously by a large fraction of the scientific community. But the question of intelligent, technological, civilization-building life is much harder. Intelligence is one thing. The development of technology, of civilization, of science, of the capacity to observe the universe and wonder about it, that may be far rarer. Or it may not. We simply do not know. The data we have is a sample size of one. But every megastructure we have described in this exploration, every filament of the cosmic web, every galaxy cluster, every quasar, every neutron star, every supernova remnant, every nebula, is also a potential environment for life. Not for life as we know it, necessarily, but for chemistry, for complexity, for the emergence of something that can observe and wonder. The universe is vast, and it has been at this for a long time. Whatever is out there, we are only beginning to have the instruments and the knowledge to look for it. And every discovery we make, every new image from a space telescope, every gravitational wave detection, every analysis of a distant galaxy's spectrum, expands our knowledge and our humility simultaneously. There is something else we should talk about before we reach our conclusion. Something that sits at the intersection of the largest and the most fundamental. We need to talk about what the universe might look like beyond what we can observe, and what the most extreme cosmological theories say about the nature of existence itself. The observable universe, as we have discussed, is a sphere approximately 93 billion light-years in diameter, centered on Earth. But there is no physical boundary at the edge of the observable universe. No wall, no edge. The universe continues beyond it, unseen, its light not yet having had time to reach us. Most cosmological models suggest that the universe extends for a vast distance beyond the observable horizon. Possibly an infinite distance. Some versions of inflationary cosmology, the leading theory for the universe's rapid early expansion, predict that inflation produced not just our universe, but an infinite number of separate bubble universes, each expanding and evolving independently. This ensemble of universes is called the multiverse. In some models, different bubble universes may have different physical constants, different numbers of dimensions, different laws of physics. Ours happen to have the right combination to allow atoms, stars, galaxies, and life to form. Others might be entirely different, or might not even have stable matter. The multiverse is a scientifically controversial concept, primarily because it is so difficult to test. If other universes are beyond our cosmic horizon, how could we ever detect them? The cold spot, as we discussed, is one proposed test, though its interpretation remains disputed. Other researchers have proposed that if two bubble universes collided in the very early universe, before the era of inflation ended, the collision might have left detectable imprints in the CMB, specific patterns of temperature variation that would distinguish a bubble collision from quantum fluctuations. No confirmed detection of such patterns has been made, but searches continue. The multiverse, if it exists, would represent the ultimate megastructure. An infinite collection of universes, each a cosmos in its own right, separated by the expanding fabric of inflation. Our observable universe, with its 93 billion light-years and 2 trillion galaxies and incomprehensible wealth of structure, would be just one tiny bubble in an ocean of bubbles. A single page in an infinite book. A single note in an endless symphony. It is a thought that can produce vertigo. And yet there is something deeply, mysteriously right about it. Because the universe, as we have seen throughout this entire exploration, operates on a principle of hierarchy. Structures within structures within structures, each level embedded in a larger context, each context embedded in a still larger one. Atoms within molecules, within cells, within organisms, within ecosystems, within planets, within solar systems, within galaxies, within galaxy groups, within superclusters, within the cosmic web, within the observable universe. It would be strange, would it not, if the universe itself were the final level? If there were nothing containing or beyond it? Perhaps the most honest thing that can be said about the megastructures of the universe is that they are a testament to what arises when simple laws of physics are given enough time, enough space, and enough raw material to work with. the law of gravity, the laws of thermodynamics, the laws of quantum mechanics, written in mathematical language that fits on a few pages, have produced, over 13.8 billion years, the entire breathtaking spectacle we have been exploring. Galaxies beyond number, stars beyond counting, black holes of incomprehensible power, neutron stars spinning at a fifth of the speed of light, a cosmic web stretching billions of light years, structures that challenge the cosmological principle itself. And somewhere in that web, on a pale blue dot orbiting an average yellow star on the outer arm of a spiral galaxy in a small cluster at the edge of a supercluster in one of 2 trillion galaxies, somewhere in all of that, a species arose. A species that looked up. A species that wondered. A species that built instruments to gather the ancient light of dying stars, to feel the ripples of colliding black holes, to trace the skeleton of the universe with radio waves and X-rays and infrared light and the ringing of pulsars. A species that is still, after thousands of years of astronomy, still finding things that take its breath away. We are the universe's capacity for wonder, made flesh. We are 13.8 billion years of cosmic evolution looking at itself in a mirror. And what it sees is extraordinary. There are things we do not yet understand. The nature of dark matter, the identity of dark energy, the physics of the universe's first instant, the origin of the largest structures and whether they violate our cosmological principle, whether the multiverse is real, whether life and intelligence are common or rare in the cosmos, whether the gravitational wave background will be fully confirmed and what it will tell us about the history of cosmic structure. Whether JWST's early results on massive early galaxies will require a revision of our theories of cosmic structure formation. These are not gaps in knowledge that embarrass science. They are the frontier, the exciting, dynamic, productive frontier where the best minds in the world are working every day, pushing our understanding further, testing it against new data, revising it, improving it. Science does not claim to know everything. It claims to have the best method ever devised for finding out. And in cosmology, that method has given us a picture of reality so vast, so strange, so beautiful, so violent, and so intricate that no human imagination could have invented it from scratch. We discovered it. The universe told us, through the language of light and gravity and mathematics, what it is and how it works. And we listened. Think about the structures we have traveled through together in this exploration. VY Canis Majoris, so vast it would swallow our solar system beyond Jupiter. The Milky Way, 400 billion stars spiraling through space for 100,000 light-years. Andromeda, 1 trillion stars, falling toward us for a meeting 4.5 billion years from now. The Virgo cluster, 1,300 galaxies bound together by gravity. Laniakea, 520 million light-years of galaxies all flowing toward the great attractor we cannot see. The Sloan Great Wall, a filament 1.4 billion light-years long. The Hercules Corona Borealis Great Wall, if real, a structure 10 billion light-years across. The cosmic web, the skeleton of reality itself, threading through every cubic megaparsec of the observable universe. And the forces and events that shape them. The Big Bang, inflation, the formation of the first stars, the blazing age of quasars, supernova explosions forging heavy elements and seeding them into the cosmos, galaxy mergers and collisions building ever larger structures, the quiet, patient pull of dark matter gathering everything into the filaments of the web, the inexorable push of dark energy separating those filaments from each other, ensuring that the universe's story has both a middle and an end. We have talked about the universe's past and its present and its future. We have touched the extreme and the sublime, the violent and the beautiful, the known and the mysterious. And we are left where we began, at the threshold of human comprehension, looking out at a darkness filled with light. But the feeling is different now, is it not? The night sky is not what it was when we started. Every point of light is a star, or a galaxy, or a quasar, or the gravitational lensing of something even further still. The darkness between the stars is not empty but filled with dark matter and dark energy and gravitational waves and the ancient microwave glow of the universe's infancy. The structure of reality, from the smallest quantum fluctuation to the largest filament of the cosmic web, is one continuous, interlocking, dynamic, astonishing system. And we are part of it. There is one more thing to say, something that may be the most important thing of all. The megastructures of the universe do not care about us. They are not aware of us. They do not know that a small, fragile, extraordinary species on a small, fragile, extraordinary planet has looked up and seen them and marveled at them and spent centuries trying to understand them. The universe is not cruel and it is not kind. It is vast and it is ancient and it operates according to laws that were in place long before we arrived and will continue long after we are gone. But the universe produced us. By whatever process, by whatever chain of physical and chemical and biological events, the universe produced beings capable of looking at it and finding it beautiful. And that, in itself, is perhaps the most astonishing megastructure of all. The capacity for awe. The capacity to stand at the edge of everything we know, to look into the darkness, and to want, desperately, hungrily, joyfully want, to understand what lies beyond. We will keep looking. We will keep building better telescopes, better detectors, better theories. We will keep finding things that surprise us, challenge us, humble us, and inspire us. The universe will keep revealing itself, slowly, patiently, inexhaustibly. And every revelation will be both an answer and a new question. Every discovery will open a new door, behind which another mystery waits. So the next time you are outside on a clear night, away from the city lights, and you look up at the sky, look carefully. That faint smudge in Andromeda is 1 trillion stars hurtling toward us. That bright band of the Milky Way is the combined light of hundreds of billions of stars, most of them hosting planets, many of them perhaps hosting worlds as complex and beautiful as our own. And beyond all of that, in every direction, further than you can see, further than any telescope has yet reached, the universe goes on. Filaments and voids and clusters and quasars and magnetars and neutron stars and black holes and all the structures we have explored today, and countless more that we have not yet discovered. The universe is not finished with us, and we are not finished with it. The greatest discoveries are still ahead. The most astonishing structures are still waiting to be found. And somewhere in the darkness, among the filaments of the cosmic web, perhaps something else is also looking up and wondering. Perhaps we are not alone in our awe. And that thought, that beautiful, haunting, exhilarating thought, is where we leave you tonight. Not with an ending, but with an opening. Not with answers, but with better questions. Not with the horizon reached, but with the horizon retreating, always calling us forward. The universe is out there. It is incomprehensibly vast. It is breathtakingly ancient. It is stranger than we can fully imagine. And it is waiting. Keep looking up.